Well, I guess I'll get started. Um, so, as I assume you all know, there will not be class on Thursday because it's Thanksgiving. Um, but next week on Tuesday is when we have our last exam, number 4 on chapters 23 through 29. That is also when worksheets 23 through 29 are due, and homework number 4 is due on Brightspace. After that, we will have presentations in class. Um, so make sure your topic has been accepted. Submit your 2 to 3 page paper on the topic to the um, section of Brightspace. So here, the semester project paper, this is where you'll submit the paper. Here is the semester project presentation. This is where you'll submit the presentation slides. You do need to submit your slides. The presentations will be in class. Make sure you have your slides ready before class. If you submit them to me as a PowerPoint, I can download them and have them ready for you to present. If you submit me to me as like a PDF, I can also have them ready for you to present. As long as I can actually open them, I can have them ready for you to present. You all have access to PowerPoint through the CCC website. So yeah. And so the presentations will start next week, Thursday, and will continue through to the end of the semester for the next 3 class days. So next week, Thursday, and all of the week after. And that will be the end of the semester. Any questions? Okay, I'm going to finish off chapter 29. And then that will be it for the lecture. This will be all the material that will be on the test. So, some of the results that were found from studies of the microwave background: the density is equal to the critical density. The age of the universe is 13.799 billion, plus or minus 0.038 billion years. There is some conflict about the age of the universe. There's another way of measuring the age of the universe that gets another answer. If you want to know the details about this conflict, that difference is called the Hubble tension. There is currently some debate going on about how possibly some of the measurements involved weren't as accurate as thought. And people are trying to see if new measurements with the new space telescopes will help resolve this issue. The microwave background has a dark energy, puts a dark energy constant at 68.5%, matter content at 31.5%, and only about 4% of the universe is ordinary matter. So let's talk about how the abundances of various elements help support the Big Bang theory. So one of the theorized things occurring during the beginning of the universe is that there was a period of time where the universe was hot enough for fusion to occur. That lasted from about 3-ish minutes to about 5-ish minutes, maybe 1-ish minute to about 5-ish minutes of the history of at the beginning of the universe. And if you put in the temperatures expected at the time we think it lasted, you can work out that about a quarter of the hydrogen that existed at the beginning of the universe would have combined, fused to form helium, much like what occurs in stars, and that gives you the base background level of about 75% hydrogen, 25% helium. And you can work this out. It's not like the easiest calculation, but it's not awful. I recall. I mean, it's beyond this course, but when I took a cosmology course many, many years ago, I believe we did it. Uh, so the process of nucleosynthesis, where you get the production of helium-4, protons and neutrons will fuse to form a deuterium nucleus. Two deuterium nuclei can fuse to make either hydrogen-free or helium-free, but it's believed that it was hydrogen-3 in this period. And then hydrogen-3 fuses with deuterium to create helium-4. And this left behind some deuterium. It didn't leave behind any hydrogen-3 because hydrogen-3 is tritium and that's naturally unstable, so it would have decayed. So protons and neutrons combined to make long-lasting helium nuclei when the universe was about 5 minutes old. And we can also make predictions about how much deuterium there would have been left over based on the density of regular matter in the universe and such. And that's one of the ways that we know about how much regular matter there is in the universe. So the Big Bang Theory prediction is that about 75% hydrogen, 25% helium by mass. This matches observations of nearly primordial gases. We see this pattern pretty much everywhere. Now, another thing that's actually evidence for the Big Bang is the fact that when we look at the night sky, it's dark. So if you're in a large forest and you look in any direction, you will see a tree, no matter where you look. Similarly, in an unchanging universe with an infinite number of stars, you would expect to see stars in every direction. And that would make the sky bright even at night. Now, in a smaller forest, where you have fewer trees and you have a border, you would eventually see empty space. So there has to be a boundary of some sort for us to have a dark sky. In a smaller forest with small numbers of trees, you can see open spaces beyond the trees. Because the night sky is dark, the universe must similarly have spaces in which we see nothing beyond stars, which means either the number of stars is finite, there's only so many stars, the universe basically has an edge, or the universe changes in a way that prevents us from seeing an infinite number of them. And from our understanding, it is the latter is true. We don't know whether or not the number of stars, the universe is finite. It might be infinite, it might be finite. We don't know. Because if it is finite, it is bigger than the area that we can see. So our ability to know, it is beyond our ability to know. So Olber's paradox is that if the universe were infinite, unchanging, and everywhere the same, then stars would cover the night sky. And Olber's paradox is resolved by the fact that the universe changes with time. If we look back out into space, we can look back to a time before there were any stars. So by giving the universe a finite age, we resolve Olber's paradox. We don't know if the universe has a finite size because we can't see far enough to tell. So the Big Bang model can explain observations we see of the universe today. Only hydrogen, helium, and a small amount of lithium were formed early in the universe. So during that early fusion, a small amount of lithium was formed, very small. A fraction of a percent. And about 25% of the hydrogen was turned into helium. The cosmic background radiation provides evidence for the Big Bang, and variations in the background tell us about the early history of the universe and how the structures we see today would have formed. So if we look at the composition of the universe, only about 1% of the universe is visible matter. Ordinary matter makes up roughly 5%. Dark matter makes up about 27-ish%. Dark energy makes up about 68%. Those numbers might be a little different. But And what we generally study in astronomy, planets, stars, nebulae, and galaxies, this is only a tiny portion of the content of the universe. We have to figure everything else out more or less indirectly. And this is why there's a lot of debate about this stuff. And our understanding of the composition has changed over the decades. Originally, we knew about ordinary visible matter and ordinary dark matter. Because we could see the visible matter, we could infer the dark matter in a number of ways. I mean, that's just like clouds of gas and stuff. It's stuff that's just not emitting light. That's in the 1970s. By the 1980s, we figured out that there had to be exotic dark matter. We worked out that there had to be something out there that couldn't be ordinary matter. And part of why we know it can't be ordinary matter is because the abundance of deuterium we see puts a limit on the amount of ordinary matter that exists. Deuterium abundance basically limits ordinary matter to about 5% of the universe. Because that nucleosynthesis process, the amount of deuterium that gets left over at the end depends on how much, like on the density of ordinary matter at the start. And so by analyzing that, we can figure out how much ordinary matter there had to be. So there had to be exotic dark matter. That's what we figured out in the 1980s. And then in the 1990s, we added the concept of dark energy once we realized that, to our best understanding, the expansion of the universe was not only expanding, the expansion was accelerating. And again, there is a whole lot of debate about that right now, but that has to do with that there's some new data and they're trying to work out the whole Hubble tension thing. And these calculations are not easy. But it's still accepted position is the universe is expanding. And there is dark energy. No one has really rejected dark energy. There's some debate about what dark energy is. So, what is this dark matter? Well, our best idea is probably something like WIMPs. These would be weakly interacting massive particles. These are massive particles that only interact through the weak force and, of course, gravity, because everything with mass has gravity. They're hard to detect because they only interact through the weak nuclear force. Things that only interact through the weak nuclear force are very difficult to detect because they very rarely interact with things. Because the weak nuclear force has very short range. So these interactions are very rare. They're proposed to exist, but they've not been detected. Measurements are ongoing to detect these particles. There's sort of two approaches. There's some attempts to directly detect the dark matter that should be around and passing through the Earth right now, with various detectors in the bottoms of mines. But again, a lot of these are based on guesses of what we think the dark matter is. And then there's some aspects of particle collider experiments where they're trying to see if we can actually generate these particles in particle colliders. And if they were generated in particle colliders, we could notice them. And dark matter is required to have been able to quickly form galaxies structure that we see in the universe. Dark matter doesn't interact except for gravity, so it could have started to form structures well before ordinary matter could have. And then ordinary matter would later gather onto that dark matter in the gravity wells and form the structures we see today. This explains the filaments and voids seen today. Our simulations of this evolution of the early universe with cold dark matter match the kind of structure we see in the actual universe. So, the history of the universe. Well, we started with a period of quantum fluctuations. We have the universe, there's just quantum noise. Those got locked into place by a period of what's called inflation. So there's a couple of issues with what we observe about the universe where that are best resolved through this concept of a short period of extremely rapid expansion called inflation that occurred probably during the gut era, so at about 10 to the minus 35 seconds. And during that period, the universe expanded by about 10 to the 50 times. And that locked in the quantum fluctuations and made it so if you look at any direction, everything is about the same temperature and made everything very flat. So the universe is very flat, which is sort of odd. And if we look at any direction, everything is about the same temperature, even though those couldn't have been in thermal contact because they're on opposite sides of the universe, visible universe. Then matter forms, then nuclear fusion occurs, then the cosmic background is produced, and stars and galaxies form, and then dark energy starts to accelerate the expansion. So here's a short video about the birth of the universe and that, including that process of inflation.
The evidence of the cosmic microwave background and the helium abundance together form strong support for the main tenets of the Big Bang theory, but other aspects of the early universe are still uncertain. For example, the hypothesis that the universe underwent an early period of inflation is important to explaining many features of the present universe, but we have only limited evidence for it to date. This evidence comes largely from careful studies of brightness variations in the cosmic microwave background, which are highly exaggerated in this image. This study reveals patterns described by the dots on this graph, which are well matched by models of patterns predicted by inflation. As studies like these continue, scientists hope to refine the details of the Big Bang theory. To recap, in this video we have described the earliest moments in time according to the Big Bang theory, explained how observations of microwaves from the sky provide evidence for the Big Bang theory, explained how observations of the helium abundance provide evidence for the Big Bang theory, and recognized that patterns in the microwave sky may be evidence for an early period of rapid expansion. I hope this will help prepare you for your follow-up reading in class time and suggest that you follow the study plan outlined.
So what key features are explained by this concept of inflation? Why do we have to have this short period of extremely rapid expansion very early in the universe's history? So some mysteries that need explaining. Where does the structure come from? We know that it can form up because of dark matter, but where did the tiny variations in the density of dark matter that led to that structure come from? Why is the overall distribution of matter throughout the universe so incredibly uniform? That's another question. And why is the density of the universe so close to the critical density? So these boil down to a couple of problems. There's the flatness problem and the horizon problem. So the flatness problem is the density of the universe is basically equal to the critical density. And if it wasn't basically equal to the critical density, structures could not have formed. So this is an issue. And then the horizon problem is this uniformity of the background radiation. So everywhere we look, the background radiation, the microwave background is more or less the same. This is indicating that areas that couldn't have been in contact because they're on opposite sides of the observable universe, so there's literally not enough time in the history of the universe for them to have been in contact, even with expansion, have at the rates we see today, have the same temperature. And the solution to both of these problems actually, can be through inflation. So the horizon problem is that the cosmic background radiation appears the same in diametrically opposite directions from the Earth, even though there hasn't been enough time since the Big Bang for these regions to be in thermal contact. So if we run back the expansion of the universe at the rate we observe it, they would have never been in contact. And the flatness problem is in order for the universe to survive this long, its density in the early stages must have differed from the critical density by no more than 1 part in 10 to the 15. It has to be incredibly close to the critical density. But and that's sort of weird. Like, why is it so close? Both of these, it turns out, can be resolved by the concept of inflation. And also where the structure comes from. An early episode of rapid inflation can solve all 3 issues. So the inflationary hypothesis is that the standard model of the universe expanding looks something like this. Steadily expanding over time. The inflationary model says during this inflation era, at about 10 to the minus 35 seconds, the universe was in fact much smaller and expanded by a factor of about 10 to the 50. This solves the horizon and the flatness problems. Some people theorize there was like a bubble that expanded and we're on that bubble. The horizon problem is solved by the fact that the regions that are now distant were in contact prior to inflation because the universe was a lot smaller. And the flatness problem is solved by the fact that that expansion would expand out, stretch out the universe like a balloon as it inflates, and the surface will get flatter. And we're only seeing a small portion of the inflated universe, and that small portion is closer to flat. So between 10 to the minus 35 and 10 to the minus 32 seconds after the Big Bang, right around the separation of the strong force, some parts of the universe may have found themselves in an extreme period of inflation, as shown in the graph. And between 10 to the minus 35 seconds, 10 to the minus 32 seconds, the size of this part of the universe expanded by a factor of about 10 to the 50. And this smoothed out the universe and locked in place the tiny quantum fluctuations that existed here. They got locked in place by that expansion. That created the structure. So inflation can make structure by stretching out tiny quantum ripples to enormous size. These ripples in density are now locked in place because they were small, but now they're much bigger. And so they're much bigger than the size of normal quantum fluctuations. They're not going to change. They get locked in place and they become the seeds for all structure in the universe. That's represented in what we see in the wiggling of the cosmic microwave background. And the microwave temperature can be nearly identical on opposite sides of the sky because there was that short period of extremely rapid expansion. So before that, these points A and B were close enough to be in thermal contact. So without inflation, there wouldn't have been enough time for light to have ever been in contact and made thermal contact because, we're seeing that, we're seeing the early history of the universe. These are the farthest away that light could travel to Earth, and the farthest away that light could travel to Earth on both sides. So, you'd need about twice the age of the universe for them to reach us, to interact with each other or longer. But with this short period of rapid inflation, light could have crossed that distance, and that resolves the issue. And the overall geometry of the universe is related closely to the total density of matter and energy, and our density is sitting pretty much exactly on the critical density. And the inflation of the universe helps resolve that because the inflation of the universe flattens out geometry. Like, we're on Earth. Earth is a ball. But to us, because Earth is a really big ball, Earth appears flat. So similarly, if we inflate the universe gets closer and closer to flat. So the inflation of the universe flattens out the overall geometry like the inflation of a balloon, causing the overall density of matter plus energy to be very close to the critical density. So in an instant of time, the universe grew by a factor of about 10 to the 50. This solves the horizon and flatness problems. Regions that are now distant were once in contact prior to this incredibly rapid expansion. And the flatness problem was resolved by the fact that we're only seeing a very small portion of an inflated universe. So the inflated universe doesn't have to have a flat structure. It just needs to be locally flat. Or in the small portion that we're seeing, it needs to be more or less flat. And that seems to be what we observe. And by analyzing the variations in the cosmic microwave background, we can find evidence for this. So did inflation really occur? We don't completely know yet, but there is some decent evidence for it. So the patterns of structure observed by the Planck satellite show us the seeds of the universe, the structure that the universe condensed around at some level. These are areas that are higher and lower density. And if we analyze those variations, the observed patterns of structure in the universe agree so far with the seeds that inflation would produce. So our models of inflation match the fluctuations we observe in the actual cosmic microwave background. So we have decent evidence that inflation actually occurred, and it is currently our best theory for the beginning of the universe. Now, our understanding of the early history of the universe has to do with the combination of various forces. So grand unified theories are about how the four fundamental forces of the universe can combine. So there are four forces in nature. The weakest of these is gravity. Then there's the weak nuclear force, the electromagnetic force, and the strong nuclear force, in order from strength from weakest to strongest. The strong nuclear force and the weak nuclear force we don't encounter very often because they both only act over very short distances. For slightly different reasons, but they fundamentally only work over short distances. And under conditions of high temperature and pressure, forces will unify. We've observed this unification for the electromagnetic force and the weak nuclear force. It's predicted for the strong nuclear force, the electromagnetic force, and the weak nuclear force in what's called a grand unified theory or a GUT by current theories, though we've never reached the actual temperatures and energies required to get them. And there's sort of some wild guessing about gravity merging. We don't really understand how that would work because so grand unified theories or theories of everything are theories that try to explain how gravity and the other forces can work together. The most famous of these is probably string theory, which has basically failed at this point because it keeps failing to make testable predictions and it's not getting anywhere. But the idea of string theory is that points of matter were replaced by one-dimensional strings that exist in an 11-dimensional space, and the vibrations of these appear in our dimension as matter, like gravity, etc. But yeah, string theory is basically dead at this point. So the general problem that is that general relativity, our theory of gravity, and quantum field theory, our theory of all the other forces, don't work together. Like their math doesn't work together. Our two theories are incompatible. General relativity describes things exactly. Quantum mechanics is based on probability field probabilities. And when we try and combine these and resolve this, there are various theories out there for quantum gravity. The most famous of these is, of course, string theory, but string theory is basically toast at this point. I should update these slides. And this is current research. Someday we may know, but no one has actually managed to work out a good theory of quantum gravity yet that makes actual testable predictions. One of the interesting ways to observe things, to think about things, is something called the anthropic principle. Are we just a lucky accident? The anthropic principle sort of says, because we are making these observations of physical laws, the physical laws have to more or less be what they are, because otherwise we wouldn't be here to observe them. And then we can start asking questions about, could there possibly be other universes without these physical laws, and what would they be like? Could the physical laws be different somewhere else? This leads to the idea of a multiverse. There's a few ways you can get multiverses. They get sort of weirder and weirder as you go on, but one idea is just if you go, you could have another bubble of, you could have another part of the universe so far away that light from it could never reach us, and that would be effectively another universe separate. You could have other universes that might be other bubbles of inflation that inflated with different physical laws. If you had other physical laws, would this lead to immediate collapse? Would they expand too fast for structures to form? What might happen there? These are just conjectures, since we'll never be able to visit these other universes. But, people get bored and start theorizing. There's a lot of ideas about possible things, and then there's some quantum stuff. There's sort of multiverses and multiverses when you start stacking up all the ideas for parallel universes. So only a small fraction of the universe is the ordinary matter we observe. The standard Big Bang model has difficulty explaining the horizon and flatness problems. The inflationary model can resolve these issues, and unified theories attempt to try to combine the four forces of nature. So all the theoretical physicists are kind of looking for a theory of quantum gravity to resolve the deep fundamental issues between general relativity and quantum field theory, which are two theories of the universe. So our understanding is that about the formation of the large-scale structure of the universe, cosmologists realized galaxies couldn't have formed just from instabilities in normal matter, because before decoupling, that point where the universe became transparent, cosmic microwave background, where we're seeing the cosmic microwave background from, background radiation kept clumps from forming. All that radiation bouncing around and interacting with stuff kept things from forming clumps. And variations in the density of matter before decoupling would have led to variations in the cosmic microwave background, and they just aren't big enough to form the structure we see in the universe today. But if there was some background matter that was forming structure, regular matter could condense onto that. Because of the overall expansion of the universe, any clumps formed by normal matter could have only had 50 to 100 times the density of their surroundings. But dark matter, being unaffected by that radiation, would have started clumping long before decoupling, as in hundreds of thousands of years before decoupling, and could have formed structure that, well, before regular matter, which then regular matter could accrete onto. So galaxies could then form around the dark matter clumps, resulting in the universe we see. So up until decoupling, the normal matter is kept even, but the dark matter clumped, and it clumps more and more, and then eventually, after decoupling, normal matter condenses onto the dark matter. And here are some simulations of a cold dark matter universe with critical density. And we get, after 14 billion years of simulation, we get structure that looks much like what we see in our universe today. And although dark matter doesn't interact directly with radiation, it will interact with the gravitational force, leading to tiny ripples in the cosmic microwave background radiation. and we observe those ripples. They are tiny. They're plus or minus 300 millikelvin, microkelvin. So we're talking, so the positive microwave background is at about 3 Kelvin. These variations, the whole variation of color here from the biggest to the smallest is plus or minus 300 microkelvin. So that's like plus or minus a 10,000th of the background radiation at the biggest. So they're very small, but they are there. So on scales larger than a few hundred megaparsecs, the universe is homogeneous and isotropic. The universe began around 14 billion years ago in a Big Bang, and the universe will either expand together forever or collapse. And the density between expansion and collapse is the critical density. A high density universe has a closed geometry, a critical universe is flat, and a low density universe is open. Our universe is sitting almost exactly on the critical density. Acceleration of the universe appears to be speeding up due to some form of dark energy. The universe is about 14 billion years old, and the cosmic microwave background is photons left over from the Big Bang. At present, the universe is dark energy dominated. At its creation, it was radiation dominated. When the temperature became low enough for atoms to form, radiation and matter decoupled, and the cosmic background radiation we see dates from that time, which is around 380,000 years after the beginning of the universe. The horizon flatness problems can be solved by inflation. The density of the universe appears to be the critical density. 2/3 of the density comes from dark energy, and dark matter makes up most of the rest. And the structure of the universe today could not have come from fluctuations in ordinary matter, but fluctuations in dark matter can account for what we see now. So that is that. That is the end of the lectures for the entire class. So remember, the test on chapters 23 through 29 will be on the 2nd. Your presentations and papers are due on the 4th. The presentations will be in class, starting on the 4th, going through the 11th. And your homework number 4 and worksheets 23 through 29 are due on the 2nd. And there will, of course, not be class on Thursday this week because it is Thanksgiving. So I will see you all next week on Tuesday on the 2nd for the exam. So do try and make sure you're there in person. Have a nice day. We're going to end early because we ran out of material, but I'm happy to answer any questions you have. And if there aren't any questions, I will just end the meeting and make sure to get these up on Brightspace. Well, I'm not seeing any questions, so I'm going to end the meeting. Again, any questions? Okay, I am ending the meeting. If you have any questions for me, you can send me an email.